Hi, everyone. We'll continue on here, and again, I'll give the housekeeping rules. Don't forget your surveys. We want to get your feedback on the presentations, the content, so we can improve these over time and make every session and every year better. And also, we'll have some time for questions and answers at the end of this seminar. Our next presentation is from Paul Brasnett, who is with Imagination Technologies based in the UK. Paul is a principal research engineer leading the team responsible for imaging, image processing, and computer vision algorithms within the PowerVR division of Imagination Tech. Prior to this, he was a senior research engineer at Mitsubishi Electric, involved in imaging and video processing, and participated in the MPEG standardization work. Paul has a PhD and Master's in Engineering degree from University of Bristol in the UK, and I'll turn it over to you.
Okay, thank you very much. Cheers. Okay, so I'm just going to talk this afternoon, about implementing convolution neural networks, and particularly focusing on inference on mobile GPUs. So just an overview of the talk. So I'm going to just give an introduction to Imagination Technologies, talk about PowerVR GPUs. We're going to look at a bit of a case study for implementing CNNs, provide some performance analysis, and some conclusions, and then there's some resources at the end. So for those people who aren't familiar with Imagination Technologies, so we're an IP company, and we've shipped just over 8 billion units have shipped containing Imagination IP. And there are three key areas that Imagination focuses on. So Sigma focus on communication processors. MIPS focus on CPU technologies, and PowerVR, which is a bit of the company I work on, focus on multimedia processors. And today we're going to be focusing on the GPU graphics processors from Imagination Technologies. So I'm referring to a mobile GPU, so it's probably worth just clarifying really what I mean by a mobile GPU. So mobile GPUs are optimized for high performance at low power. And although I'm sort of referring to it as a mobile GPU, you find our GPUs in a range of embedded markets, so from mobiles and tablets to wearables, IoT, augmented reality, consumer multimedia, and automotive are all the markets you can expect to find our GPUs in today. So why should people consider using a mobile GPU for vision processing? Well, so mobile CPUs can provide high peak performance, but can also generate significant amounts of heat. So PowerVR GPUs, we focus on providing very efficient use of resources. So we have low power, half precision, and also integer support. Have a GPU, and our GPUs have local memory for very efficient data accesses for compute operations, and also we have the ability to power down parts of the GPU that are dedicated to graphics. So if you're running compute tasks, you can power down the hardware powers down the graphics parts, so that helps to save energy. And this graph just kind of gives an example of for compute tasks across a range of different compute tasks, the performance gains you can get by moving from a mobile CPU to a mobile GPU. So we can see somewhere between 2.5 and 11x performance gains moving from a CPU to a GPU. And it's good to just think about what the difference is between GPU and a CPU. So CPUs typically have a very large cache and work to keep the compute units busy. And they're typically very good for tasks that have very serial dependencies and conditional branches. GPUs, on the other hand, use a significant number of threads, and they're able to switch between tasks while they're waiting for memory to return, which allows them to to dedicate more of the area of a GPU, or more of the area of the GPU to the compute rather than to very large caches. And so the nature of a GPU, that it is good for very highly parallel code and code that doesn't have significant conditional branches, maps very well to the sort of workloads that we see for CNNs. So just the kind of the evolution of where PowerVR is with mobile GPUs. So Series 6 GPUs are our first GPUs that were kind of pretty compute capable. And those are several years old now. So we moved through Series 7. And some of the key things in Series 7 were improved 8-bit and 16-bit integer performance. And then kind of we're moving on to Series 8 GPUs now. And we kind of focus on improving the compute performance. And vision is one of the key tasks that we focus on, trying to improve the performance per milliwatt and per millimeter squared. And it's worth just saying that PowerVR GPUs are very scalable, so they scale from a few hundred milliwatts as the lowest power up to low orders of watts, and you get up to sort of a teraflop of performance within that envelope. So they scale from very low power up to very high performance. There's been an evolution of API standards for compute and for vision, and we continue to support that. So the latest GPUs are supporting OpenCL2. We have OpenVX conformance, working on Vulkan. So we continue to make sure that the GPUs meet the market requirements for APIs. And just lastly, on the side, from the side of GPUs, just want to point out that we see a trend where GPUs are increasingly dominating the amount of compute performance in an SoC. And this is generally driven by graphics demands. But as people working in computer vision, it provides very useful and significant amounts of performance that it's worth considering when you're looking to use and deploy vision solutions. So we'll now just move on to looking at CNNs. I think it's sort of been pretty well reported that CNNs provide state-of-the-art performance for a number of vision tasks, particularly classification. For the last few years, we've seen significant progress in the area of classification. But another thing that CNNs provide is kind of rapid development cycles. With traditional computer vision, it's very research intensive to find solutions to problems, and often solutions are kind of point solutions for particular problems. CNNs provide a more generalized approach, and you can, with a good data set, you can make significant progress very quickly. And we're also seeing that CNNs are making good progress on other vision tasks beyond classification. So the example we've got here is for camera localization. So being able to locate from a single image, locate where a camera is and what direction it's facing. And that's showing kind of a very high performance using CNNs, which is maybe an area that you wouldn't expect CNNs to perform well. So I'm not going to spend a lot of time looking at what a CNN is. I think it's been covered well elsewhere in this session. But just to briefly say, we've got a set of building blocks. And we can combine the building blocks in some way to define the architecture that we want. So at the top, we've got our kind of the key representative building blocks, and then an example network there. And I would just want to talk a bit about the sort of the life cycle of CNNs. And here we're talking about classification. So there are two key phases in the life cycle of CNNs. The first is training. And training is it's an offline process and typically done a small number of times. You're not looking to repeat it a vast number of times. The input to the training process is your architecture, so a definition of your architecture, and your data, so some training data. And typically you would use some library. So earlier we heard about TensorFlow. Yesterday was a tutorial on Caffe. There are numerous other libraries out there. And then you add in some compute, which often is a desktop GPU, and then some time. And then out of that you get your model coefficients, which is your trained network. And then kind of the second stage of the life cycle of CNNs is the deployment. And this is kind of where we're focusing for the sort of mobile and embedded area. And so Inference is typically online. So you're very interested in high performance and quick response times. But it's something that's repeated a large number of times. So we're interested in maximum efficiency. And so what we can see is from the training stage, we get, when we're online, we get our architecture, get model coefficients, and then we need our input image. Again, we use a CNN library, so we're looking to reuse the same sort of processes from training. And then we have some compute for our inference, and here we're looking at mobile GPUs to perform the compute. And out of the end, you get some classification. So we're looking at CNNs. It's worth looking at where we should be spending our effort to optimize CNNs. So here, if we look at the operations by kind of, we've got sort of four of the key layer types that add to the cost of a CNN. And this is for AlexNet. You can see that the floating point operations or operations, if you choose to do it in fixed point, is dominated by the convolution operation. So we're just going to look a bit at how to optimize convolutions. And particularly, people will often use a matrix multiplication as a way of implementing convolution. So if we look at how to implement matrix multiplication, so you've got a naive approach to matrix multiplication, which if we're trying to multiply matrix A and matrix B to get our output matrix C, you could create as many work items by mean threads, as you have in your output C, and each one reads a row from A and a column from B and generates an output in C. The problem with this sort of approach is that it requires a very large number of memory accesses, and memory accesses are slow and burn power on an embedded platform. So what we can do is use the memory hierarchy in a GPU to improve the performance. So here we're kind of using the OpenCL memory model, which maps well to a GPU. And there are three key levels of memory in the hierarchy. So we have private memory at the top, and private memory is typically small, but very fast, and accessed by just a single thread. And then we have local memory, which is shared across a group of threads. It's typically larger than private memory, but is typically somewhat slower and more restricted than private memory. And then we move to global memory. And here on the chart here, we've got global memory and host memory. And in an embedded environment, typically the CPU and GPU have unified memory, so we don't have this divide. So with global memory, it's typically the largest memory that you would have, but it's also slow with large latencies. So if we look at how to implement matrix multiplication using the knowledge of the GPU hierarchy. So we're multiplying A and B to get C again, but this time each thread or work item will output a set of values in C. And it does that by loading data from A into its private memory. And then a group of work items will load data from B into local memory. And then each thread, as it's generating its outputs in C, needs to read data from its private memory for A, from the local memory for B, and output the data to C. And this helps to significantly reduce the number of global memory accesses, which helps to significantly improve the performance. So we'll see some results in a minute, but just some tips on implementing for PowerVR GPUs. So it's important to choose the workgroup size to fit the GPU. And for PowerVR, typically 32 work items is a good choice. When you're reading into private memory, it's useful to read multiple items at a time. So 4 or 8 items help to optimize memory transfers. It's worth considering using half precision data type. So most PowerVR GPUs provide up to twice the half precision floating point as single precision floating point. And you can also, if you define the workgroup size at compile time, it helps the compiler to do a better job. And if we kind of put these things together, what we see is that we get sort of almost a 2 orders of magnitude improvement between a naive implementation and a somewhat smarter implementation. So very significant gains to be had. So I'm going to look now at what does this mean in terms of performance for the overall CNN when you're looking to deploy it. So we're going to focus on 2 well-known networks, AlexNet and GoogleNet. And so we've got the error rate of GoogleNet is significantly lower than the error rate for AlexNet. And here, if we look at kind of some of the reasons why, so what GoogleNet does is uses significantly fewer model coefficients than AlexNet, but it's also somewhat higher compute. So there's the model coefficients leads to a significant reduction in bandwidth, but what GoogleNet does is trades that off for compute, and that helps it to achieve a much better performance. So if we look at the amount of time consumed by the 4 key layer types that I've been focusing on, we can see that for AlexNet, a significant amount of time is spent on the fully connected layers. For GoogleNet, more time is spent on the convolutions. And if we look here at the bottom, we've got sort of reference time comparing how long it takes to run an AlexNet for a single image of AlexNet compared to a single image for GoogleNet. And it's about 35% longer for GoogleNet, but we saw from the previous slide, it's actually about 2.5 times the amount of compute. So AlexNet's kind of is making more efficient use of the resources available. And what we can also do is compare the performance of a PowerVR mobile GPU. So here the GPU is running at 480 megahertz compared to a CPU running at 1.6 gigahertz, so significantly slower. It's a single thread running on the GPU. And what we can see is somewhere between 4 and 12x more performance available from the GPU than the CPU. And what we also did was to look at it. One of the arguments is potentially that the GPU is larger than the CPU. So here we've normalized for area. It's maybe not the most representative metric because the GPU has a lot of area dedicated to graphics, but just to give an idea of what happens when you do normalize for area, we can see that we're still getting sort of up to 3x performance improvement on some of the layers. Okay, so sort of reaching the end of the talk. So just to recap, that I've talked about PowerVR GPUs, mobile GPUs, and really they're found across a range of embedded markets. And I've shown that mobile CPUs can offer somewhere between 3x or up to 3x higher efficiency for area and up to sort of 12x higher performance, absolute performance on a particular platform that we measured these results on. Newer CNN architectures with smaller fully connected layers like GoogleNet make much better use of the compute resources. So we saw that although it's 2.5 times the amount of compute, it only takes 35% longer to run on GPU. And just to summarize, so PowerVR GPUs scale from very low power, so from a few hundred milliwatts up to single figure watts and all the way up to sort of 1 teraflop in performance. We've got a demo just back there. If you look for the purple tablecloth, we have CNNs running on PowerVR GPUs. And come and see us during the next break. There's some links here, which I'll leave up, and happy to answer any questions that people have.
We'll give people a chance to step up to the microphone. Thanks, great presentation. I'll start with a question. So GPUs, it's understandable from a mobile device standpoint. There's a lot of discussion about the classification being done on the mobile device, and that's great. But GPUs are also well known to be used for training. So where do you see that heading in the future in terms of being able to do training remotely, where a drone can retrain itself, or devices that have embedded GPUs can be used for retraining,
Absolutely.
for training, not just classification?
So it's something that we're looking at, and it's very viable as a solution. As you say, desktop GPUs are being used today. It would make perfect sense to be able to use a mobile GPU in the same way. They're essentially very similar in architecture and capabilities, just slightly different optimization points. But yeah, I think that's something perfectly capable.
Okay. Any other questions?
Is the support for OpenVX in the roadmap?
Sorry?
Support. The question is there any support for OpenVX planned in the roadmap?
Yeah. So our GPUs, we have OpenVX conformance for our GPUs today. So we have on the stand just back there, we have OpenVX demos running. So yeah, it's something that's available right now.
Right. Any other questions? Okay, thanks again. Great presentation. Appreciate it.